So hi, let us now briefly review the Parker solar wind solution and comment on a few facts. We've already commented on a few complications to the Parker solar wind solution. The fact that although it's a nice elegant solution, in reality there are several issues associated with it, and several other issues such as magnetic fields and so on and so forth, right? And but let us now consider a couple of other aspects, right? So just to recap, this is the way a typical transonic Parker solution, the ideal Parker solution looks like. So this would be increasing radius from the center. So the sun would be essentially at the center, and on the y-axis you have the Mach number square, and these are solutions of the kind 2. We saw all the solutions together on the same graph. Now we are concentrating only on the solar wind solution. So this would represent the solar wind solution, right? And so what does this represent? Well, so the Mach number is plotted on the y-axis, and this is where Mach number equals 1. So this represents a kind of solution which starts out subsonic at the very center, right? Okay, you might wonder, at the very center you see, because we are taking Newtonian gravity, which goes as 1 over r, exactly at r equals 0 the gravity blows up. So what's the problem? So that there would be a problem. Let us sort of sidestep that problem. Let us not go to the very center of the sun. Let us simply say that these represent very small radii, okay, say 1 solar radii or something like that, 1 solar radius. Just for context, the sun is 1 solar radius. That's about 1 solar radius is about 6.96 times 10 raised to 10 centimeter, and the sun earth distance is 215 solar radii. Okay, so we are 215 solar radii, roughly speaking, away from the sun, and this is typically called 1 astronomical unit. Okay, this 215 solar radii, this is typically called 1 astronomical unit. Just to tell you that 1 solar radii is really very small, even in the context of the inner solar system, although it's 6.96 times 10 raised to 10 centimeters, so it's quite large. And the earth would fit very easily, lots and lots of earths would fit very easily into the sun, but by way of distances in the solar system it's really quite small, because 215 suns could fit in between the sun to the earth. Okay, so that's the context, that's the kind of picture you should have in your mind while those are the kinds of numbers you should have in your mind while looking at this x-axis, right? So this would be a transonic solar wind solution, right? Okay, why transonic? Because it passes smoothly through the sonic point. This is where the sonic point is. Now, before proceeding, you should realize that this is radius in spherical coordinates. So it's just radius. So when we say sonic point, we really mean a sonic surface. Okay, a spherically symmetric sonic surface where the Mach number passes smoothly through 1. Okay, now the one thing, everything that I will be talking about right now comes from the following paper, Shivamogi et al. And so I should give Shivamogi and Rollins, and this can be downloaded from the this can be downloaded from this site, and the reference is 1905 dot 0363. This is the reference. Okay. So this is where I'm getting the material where I'm talking about right now. This is very recent, so I thought I would, this is a research paper, so I thought I would discuss the gist of this research paper for a little bit. Okay. Now remember, the traditional Parker solution uses the isothermal sound speed. Okay, where P is related to rho using P equals A naught squared rho, where A naught is the isothermal sound speed. This is how we did our derivation. Okay. And another way of writing it is if you use a polytropic relation between P and rho, and we write P equals C rho raised to gamma, gamma equals 1 is isothermal, gamma equals 5/3 is adiabatic. Okay. Okay. And in using this kind of sound speed, we are assuming gamma equals 1, of course, and that's what the traditional Parker's definition uses. In general, of course, gamma is somewhere in between 1 and 5/3. Okay, and C is of course an arbitrary constant. So this is the general polytropic relation, and we will see what this paper does is it investigates the effect of a polytropic equation of state on the solar wind solution. Does the solar wind solution become faster? So, on Parker's solar wind solution. That's what this paper does. In other words, it tries to see if this gamma was not exactly equal to 1, yeah, if it was between 1 and 5/3, what happens? Okay. Now, why are we so interested? Why is this problem even interesting? People write papers, people, come up with interesting mathematical consequences and so on and so forth, but it's very important to know, to figure out why it's interesting. Why is this even worth paying attention to, right? The reason it's worth paying attention to is because, the polytropic, the equation of state, this one is actually kind of an energy equation. If you remember, we never used the energy equation anywhere in deriving the transonic solution. We only use the conservation of mass and the conservation of momentum. Those are the only two equations we used. It's only via this kind of a closure relation between P and rho that we introduce the idea of energy conservation. And why is this energy equation important? Or why is it that we even need to investigate anything other than this? That is because observations reveal, right? Observations reveal that the velocity profile predicted by Parker's isothermal, this kind of solar wind solution, are a little too low in comparison to observations. Okay. And the temperatures In particular, the temperatures are a little too low in comparison to what this kind of Parker solar wind solution together with this kind of a relation predicts. Okay. So, the net upshot is that observations suggest that there is some kind of additional or distributed energy deposition, deposition in the solar wind over and above what a Parker solution predicts. Parker solution simply takes a very hot solar wind and it lets it cool. Okay. As the solar wind cools, it accelerates. The thermal energy is converted losslessly, so to speak, is converted nicely into the bulk kinetic energy of the flow. That is what this solution with the isothermal equation of state predicts. Now, turns out that this doesn't quite, agree with the observations. Observations suggest that there is some kind of additional and by distributed I mean all throughout the solar wind. That's what I mean, all throughout the solar wind, as in it's not at one radius or two radii or so on and so forth. It seems like there is some additional energy deposition for a while as the wind flows out. Okay. So, and this can be captured via a polytropic equation of state like this, okay, in particular by varying the value of gamma. Okay. So, that is it really. So, the upshot is that one goes through this entire exercise and says, instead of writing and I beg your pardon, instead of writing P equals A naught squared rho, we write A squared equals dP d rho equals gamma P over rho. We write this. So, this would be a new definition of sound speed, okay, where the gamma can be between 5/3 and 1. All right. And then one goes through the entire derivation just like that, no difference. Okay. One just goes through the derivations as it is, and the upshot is essentially, I am not going to reproduce the entire all the calculations, but the upshot is a graph something that looks something like this. The net result is a graph that looks something like this. You would have R normalized to some and this would be the Mach number, and all the solutions like this, and this would be, for instance, this would be gamma equals 1, okay, this curve, okay, and in this direction you would have increasing gamma. Okay. So, this would be the isothermal, this is the original Parker wind solution. Okay. This kind of a curve, and if you increase the value of gamma to above 1, remember the adiabatic is gamma equals 5/3, which is something like 2.2 odd, and if you increase the gamma even a little bit, okay, something like 1.1 or 1.01 and 1.1 or something, what happens is, what you find is that the Mach number increases. You can see that the Mach number for this solution is larger than the Mach number for this solution. And what distinguishes this from this? The gamma here, the gamma for this solution is slightly larger than the gamma for this solution. Okay. So, what the upshot, the main conclusion of this paper is that increasing gamma leads to faster and more tenuous solar wind flows. Why faster? Well, here you go. This is what the solutions look like. So, you increase gamma from here to here, and clearly for a given radius, the Mach number here is larger than the Mach number here, and the Mach number here is even larger than the Mach number here. So, that justifies this. And if you go through the solutions again, you will find that the densities, when you increase the gamma, the densities drop. In other words, the solar wind solutions are more tenuous. Okay, and these kind of agree with observations. Okay, so this is one modification from the standard Parker wind solution that I thought I would point out. There are some other interesting modifications, okay, and I will discuss them one by one. The other interesting modification has to do with solar rotation. Okay. Now, what about this? You see, Parker solar wind solution assumes one steady state, which is to say, if you remember, nowhere we essentially all these partial over partial t's were all taken to be 0 in all our equations, if you remember. Okay. So, that is what I mean by steady state, and a non-rotating sun, right. This is what Parker's solution assumes. It assumes that you have steady state, and that is true for all the solutions that we discussed. Steady, this is common, and we are not going to relax this in what we are discussing now, but we are going to try to examine the effects of the fact that the sun actually rotates. It is well observed. It is well observed that the sun is not stationary, and it is actually rotating. This is well known. Okay. So, what about it? So, how would it possibly modify this whole thing? And also the fact that the other thing is Parker's solution also assumes that the wind starts from rest. In other words, the initial velocity of the solar wind is strictly equal to 0. That is the reason a traditional solution, this kind of solution actually starts from 0. But surely that is not the case. Okay, surely, because there is some finite pressure, the wind cannot be starting from 0. So, the following discussion is taken from a paper also by Shivamogi, but it is a different paper. Okay, and it can be again downloaded from right. So, this can also be downloaded from the archive, right. So, suppose let us relax this assumption first. Let us relax this assumption, the fact that the wind starts from rest. Let us relax this assumption. And how are we going to relax this assumption? Well, in the following way. What we are going to say is that instead of, let us write the density as a function of radius, and now instead of taking a strictly stationary solution, let us allow the density to be a function of t via the following manner. The background density is still steady state, but we introduce a small perturbation, right. The density and the velocity is also a function of the radius and of time, and that is, we assume that there is a very small velocity which is a function of r, and it is a function of time through this. This is the assumption. Okay. So, what is the deal here? You have a background density and you have a perturbation. So, rho naught, this and this are small perturbations. Okay. And we know, while linearizing and everything, we know what the meaning of this word is, small perturbations. We know this. In other words, this entire term is very small in comparison with this. So, we allow for the fact that the solar wind starts with a small velocity v hat from the surface, okay, and we see what happens. Okay. So, what we do is, instead of in the mass and momentum conservation equation, we substitute this rho and this v. Okay. And we know that the background density satisfies the background equations, and it was assumed that the starting velocity was 0. Okay. So, now the starting velocity is some small quantity. So, what we would do is, one would find out evolution, the logic of this is, one finds out the evolution, the time evolution equations for the perturbed density and the perturbed velocity. Okay. And the main finding is that omega is real. What does this mean? Let us look at this equation again. Omega is real, and this is the assumption. So, if omega is real, this is oscillatory, the e raised to I omega t, this is oscillatory. What if omega was not real? If omega was not real, this would not be oscillatory, this would be either a growing or a damped solution. And in particular, if it was a growing solution, there would be a problem. If it was a growing solution, what it would imply is that the presence of a non-zero velocity, okay, if it was a growing solution, in other words, if omega was not real, if it had a complex part, it would imply that the presence of a finite starting velocity is enough to render the Parker solution unstable. Okay. Whereas that is not the case, omega is real, therefore, the solution is stable, time stable, in the sense that as a function of time, the small perturbation does not grow. Okay. It only oscillates, it does not grow with time. Okay. So, in that sense, these perturbations are stable, and so therefore, you can allow for a finite starting velocity. This is the main upshot of this discussion. The other upshot of the discussion, the other main thing about the discussion is how to include rotation. How to include rotation. The way you include rotation is you modify the momentum equation, which to look like the sound speed is generally called A in this paper. So, I am simply writing A. So, A is essentially what we used to call CS squared. Okay. So, this would essentially be the this would be the pressure gradient term. So, this entire thing is MA, of course. This would be the pressure gradient term, and you don't see pressure because you have the sound speed, so it's expressed in terms of the density. We've seen all this earlier, and M sun, this would be the gravity term, right? And now you have a very important addition. You have a centrifugal term. This is due to rotation. This term is due to rotation, and omega star is the rotational velocity of the sun. This is how you include rotation. Okay. Now, the recipe is the same. You assume this kind of solution. Okay. You assume a small perturbation in density, and you assume a small perturbation in velocity, and you put it through the two equations, mass conservation and momentum conservation, except now the momentum conservation equation is modified like this. And the finding, the main finding is that omega is again real. So, solutions including solar wind, solar rotation are also stable for the same reason, because you look at this, because omega is real, the perturbations are only oscillatory, they are not growing or damping without, in particular growing is the thing that we are focusing on. The perturbations are not growing without bound, and therefore the solutions are stable. So, these are the two modifications to the Parker solar wind solution. Spherically symmetric, again, we are not considering the effects of magnetic field which disturbs spherical symmetry. We talked about this the last time, that there is a fast solar wind and a slow solar wind, but here I thought I would present these couple of interesting results that were published quite recently, and these include the effects of a non-zero starting velocity, and includes the effect of solar rotation, and tries to investigate the effects of these physical situations on the stability of Parker solar wind solution. Thank you.